Okay, now should we start, Jobir? Yes?
Yes, yes, you can
Okay.
start.
You may share your screen, William.
Okay, well, all right. So I guess now everything is supposed to be just fine. Just let me know. Are you
Okay.
guys seeing my screen?
Yes.
Okay, great,
Now,
great.
now we are seeing your screen. Yeah. Okay. So today we have a very interesting talk. I'm not saying this because I am a co-author. It's because it's very interesting. By Willian Franca from Brazil. He's based in Juiz de Fora, and he's going to talk about applications of compact multipliers to algebrability of L infinity minus Z0 and BL2 minus KL0 union 0. Yeah, so William, whenever you want, you may start.
All right. All right. Thank you very much for the presentation. I also want to thank the organizers for giving me this opportunity of being here today to give this talk. So as Jorge said, I'm going to talk a little bit about application of compact multipliers to algebrability. All right, so what I have planned for today is to, in some sense, to present a general scheme, right? How the results were actually obtained, because there are so many technical details, and I don't want overwhelm or maybe bore you. I mean the audience with so many technical details. However, I'm gonna, to present some basic definitions and for sure the main results, right? And keep in mind that maybe some definitions, maybe I could make some references, just in case, to point out some interesting properties, maybe some relevant information, or to obtain the results. So, the abstract says pretty much this. We will be basically work with separable things, right? Separable algebras, right? One class of the algebras are going to be what are so-called the uniform algebras, all right? And the other one is the so-called C-star algebras, right? Essentially, we are going to be interested in these classes when they don't have any sort of compact elements. I'm going to explain this, throughout the talking. But the main idea is going to be the following. If you choose any algebra in the such class, with no compact elements, we are going to show, that it is possible to construct, an algebraic isomorphism. In the case of C-star algebras, the isomorphism is also, a star isomorphism, okay, between the algebra and some, subalgebra, which is contained precisely, in the complement of the C0, right, union 0, okay? And from our methods, we are going to be able to, to consider, certain algebras and in terms of, there's multi-cardinality possible of a set of generators, right? And we will also be able to generalize one very famous result, which is due by Nagisa, right? Which talks about some sort of embedding, right? But, I'll explain the details throughout the talking. So let me start. Essentially, the talk is divided in three parts, right? We are going to start with notation and the preliminary result. Actually, such preliminary result is the only result that I'm going to, provide the details of the proof, right? Because it is a short proof, all right? And also because, such proof is the starting point of our whole investigation, all right? So let's have some basic notations and, basic definitions. For now, X and Y are two Banach spaces. Okay, so by Banach space, I mean, a normative vector space which is complete, right? We are going to denote by BXY, the algebra of all continuous linear mappings from X to Y. Okay, and all continuous in the linear mappings. Okay, so we are not assuming any sort of extra structure. It is well known that Pxy is Banach space, right? When endowed with the norm, which is this what is the so-called sup norm, okay? Which is precisely the sup of the image, the T of x, or the norm of T of x, when x belongs to the unit ball of the domain. All right. And as usual, we're gonna write k of xy. Just be careful because we are gonna have another kind of k throughout the talk. So this k is kind of stylish. So in this case, k of xy represent the set of all compactor operators. Okay. And let me just recall one thing. We say that operator is compact. Okay. When the norm close, the norm closure of the image of the ball is a compact set. All right. And in a similar fashion, we can define weakly compact operators. And just because, T of B of X is a convex set, we can also, consider the same strong closure. We don't have to consider the weak closure. So the only difference now is we ask for this set to be weakly compact. So that makes our lives a little bit simpler. Okay, in the usual, in case x equals y, we have the convention just to write b of x. All right, and in this case, b of x becomes a Banach algebra with exactly this, the same norm. All right, so since the operators are from x to itself, so that makes sense to consider the compositions, and where the product in this case is going to be the composition. Okay, and in the same fashion, k of xx we are just gonna denote by k of x. So they are both Banach algebras. Now let me present some more definitions. Let A be a Banach algebras. Let me make one thing very clear throughout the talk. All of our algebras are associative. Okay, so a Banach algebra is essentially what is a Banach space, all right, where the norm is what we call the multiplicative norm. What that means, the norm of the product is less or equal than the product of the norms of the two elements. Okay, and so for a Banach algebra, we may define the operator L of A, which is essentially the lefty multiplication. Okay. And those operators, we call them lefty multipliers. So in case you note that our algebra is unital, you can actually show that the norm of such operator is exactly the norm of the operator, a norm of the element that generates such operators. So on this mirror, so we're going to say that A is a compact lefty multiplier if the associated, lefty multiplier is a compact operator. So following exactly this definition. And the same way, we may define weakly compact, right? And everything we do for the left, we can also do for the right. Okay, so we don't have to keep, introducing more definitions, but work in the same way. All right. And as I said from the beginning, from time to time in the definitions, we are gonna point out some relevant facts. Okay. So and if by any chance wants to know a little bit more about the references, we can discuss, or I can actually I can just show the reference by the end of the talk. Okay, but the thing I want to point out is the following. A is a weakly compact left multiplier in a C-star algebra. That means that A is also weakly compact right multiplier, and vice versa. So if you have the property from one side, you have to the other side as well, in the case of the weakly compact left multipliers. All right. Now another definition. Just don't get confused with the previous one where we introduced multiplies by left and the right. Here you're saying that an element is compact, whereas this operator, when you have the multiply by the same element in the both sides, is actually compact. Okay. Oh, sorry. And we're going to denote by k of A. Just be careful because now my k is not stylish. So that means I'm going to be focusing in just the compact elements. So of the Banach algebra. So as again, after applying some results, it is possible to show that if A is a sister algebra, so an element is a compact, if only if A is a weakly compact left, so that means also right multiplier, okay? It is also known that K of A is a numerical closed two-sided D of A. All right, so I'm just providing the references, so in case anyone becomes interested, I can show you by the end. Now let's prove the only result that we're gonna actually present the details, right? It is the following result. If we have, a bounded isomorphism of Banach algebras, that means what? A and B are two Banach algebras, okay? Which is my application phi is linear and continuous, right? And it's also multiplicative. So it preserves multiplication. So in this case, if you fix an element in the algebra A, so we have the following conclusions. If A is compact in A, if only if the image is a compact element in B. So in this case, I'm talking about compact in this sense, all right? So when I multiply them in both sides. The same works for left or right compact multipliers, okay? A is a left or right compact multiplier, if only if its image is also a left or right compact multiplier. So the proof is quite short, okay? We only need to prove one because the proof of two is very similar. So we may assume, for instance, that A is a compact element. So now choose bounded sequence in B. So from the continuity of the inverse of the map, okay, we can we can show that the image of this sequence BK, by the inverse, is also bounded sequence. All right. Now, using the fact that the A is a compact element, so the associated operator U of A is compact. So UA of CK, or it converges itself, or in the worst case scenario, possesses a subsequence which converges. So now we can just apply the map phi in this in this expression and using the fact that phi is multiplicative, so we can realize that the phi of A is actually a compact element in B. Okay, so the proof is very short. All right, there are no tricks, and it's pretty much standard. All right, but this, is essentially our starting point. I'm sorry, what have I done? Okay. Now let's, introduce a little bit more of, definitions. So if you have a commutative Banach algebra, so we are going to call the spectrum or structure space or maximal idea space. You can find all this nomenclature on the literature as the set formed by all continuous linear, linear functionals. Okay, by linear function I mean a map that which domain is the algebra A, and whose image is contained in the scalars. In this case, for us everything is complex. So we are considering maps which are linear from A to C, which is also multiplicative. All right. It is usual, to consider, the spectrum with the weak star topology. All right. Just to recall that in this case, the weak star topology is pretty much, the pointwise topology, where your convergence, is based on the by point. You're considering, a net converge into another function if converges pointwise. Okay. One point to note is the following. If you remove the commutative here, there are examples where this set is actually empty. So for commutative Banach algebras, we can always sort of assume that this guy is not empty. So that's the one thing that's important to mention. Okay, and another thing which is somewhat quite well known for at least for people that work in this field is that the spectrum is a locally compact Hausdorff space when equipped with the weak star topology. Okay, and it becomes compact in case A is unital. So we do have this piece of information as well. Now let me just to present one more definition. Okay, um, let L be a locally compact Hausdorff space. Okay, and as usual, C of L stands for the set formed by all continuous functions from L to C. Okay, we say that a function vanishes at the infinity when for each positive number, okay, we can find a compact set, all right, where your function is, controlled by epsilon whenever x is not in K, all right? So from now on, we write C0 of L to represent the set formed by all functions that vanish at the infinity, all right? One thing that's really important to mention is the following, okay? C0L is actually a C star algebra, right? Where in this case, the involution is essentially the complex conjugation, all right? And another thing that we should mention here is that, any commutative, C star algebra, we can be identified with a space of this form, where in this case, L is essentially the spectrum of the algebra. All right. And if the C star algebra is unital, so that means that the spectrum is compact. So you have essentially C of K. All right. Just one more thing. Okay. We're gonna denote by CB of L the algebra of all bounded continuous functions of L, which is also a unit of C star algebra. Okay. So this is, the basic definitions, and notation, for us for now, right? And another thing that we should mention is the following. Okay, it is well known, all right, if you consider a semi-simple commutative Banach algebra, so the Gelfand transform, which is essentially this map, all right, which has the domain in A, and which image is contained in C0 of the spectrum, okay, is a contract, okay, injective homomorphism, okay. The injectivity is because it is semi-simple, all right. Otherwise, maybe it's not even injective, okay. Um, However, we cannot guarantee, beforehand, that we do have as we do not have, reasons to believe that the map is isometric, all right. However, in case that your algebra satisfies this condition, okay. Or in other words, when your algebra is a uniform algebra, the Gelfand transform is isometric. So for us, just to make clear, your uniform algebra is a semi-simple commutative Banach algebra which satisfies this condition. All right. So besides, in case A is a abelian C star algebra, the Gelfand transform is a star isomorphism. As I have mentioned before, abelian C star algebras are essentially space like this, Okay, let me see what else I should mention. Oh, another point. In addition, the existence of compact elements in commutative C star algebras is linked with the existence of isolated points in the spectrum. Okay, this fact actually is also true for uniform algebras, and as I'm going to state in the sequence. So if A is a uniform algebra, so K of A, I mean the set of compact elements of your uniform algebra A is zero if and only if the spectrum has no isolated points. So this is also known. Okay. Now, finally, I believe now we're pretty much done, with the basic, information needed. So if you assume that we have a separable Banach space, okay, the following fact is classical in the theory for Banach space, right? You can always, find, a sequence in the topological dual of your separable Banach space with the following property, okay, where the norm, okay, of each element is exactly this supremum, right? That holds for every element of your Banach space, okay. So from this, we can actually, construct a linear map, okay, from X to L infinity, all right? And this map is an isometric isomorphism, okay, between X and the closed subspace of L infinity, all right? So if in the case, you have a separable Banach space, so you can actually construct such map. However, you have no recollection or prior knowledge where exactly, the image of such transformation is laying down. You don't know, you have no knowledge about whatsoever where where the image is going. So this, essentially this is going to be the starting point of our investigation. Okay. So let me just, make things clear. So we can show the following. If A is a separable Banach algebra and T of A to L infinity is a multiplicative isometry, if the set of compact elements of A is restricted to 0, so the image is contained exactly in the complement of C0 in union 0. So in particular, A is isometrically isomorphic to a closed subalgebra of such set. All right, so now what we're going to do in the sequence, we want to find scenarios where we could apply this, this general principle. Which principle is exactly the one that's presented in the theorem. So we want to find settings where we can guarantee the existence, of multiplicative isometry, right, from A to L infinity. So from the previous discussion, it seems to be reasonable to consider separable Banach spaces, in this case, separable Banach algebras. All right. So let's see what we can do. All right. However, since we needed, to consider, separable Banach algebras, so the first question that may pop in our minds is when, what kind of conditions we may impose, in order to assure that certain algebra is separable. All right. Just I don't know if I have mentioned, okay, but when you say that algebra, not Banach algebra necessarily, Banach space by separability, I mean, it contains a countable, dense subset. Okay, so we do have, a subset which is countable and dense. All right. So, as I said, before that to this problem, we present the criterion for separability of commutative Banach algebras in terms of their maximal ideal space, or in terms of its spectrum. So, if you have a commutative semi-simple Banach algebra, then A is separable if only if, C0 of the spectrum is also separable, right? So you do have a somewhat, a criteria to decide if a commutative semi-simple Banach algebra, is separable or not, okay? In terms, of this associated space, which is related to the Gelfand transform, all right? Just to remind you, this is the Gelfand transform. So you are answering about separability on A from separability to C0 of delta A, okay? So, as I said, we're going to add some piece of information, just, to give you some taste from the information, and the techniques you're somewhat forced to use, in order to obtain the results. Okay, some of the results, we have obtained combining things we have proved with some other ones. So A commutative semi-simple Banach algebra is separable if only if its spectrum is metrizable and separable if only if its spectrum is sigma compact, and metrizable if only if its spectrum is second quantum. So we do have a lot of topological properties behind it. So that's the thing you guys should keep in mind. There's not some sort of analytical approach, okay, but there are so many topological ideas behind it. So now using this basic setting, we are able to prove the following theorem. If you have a uniform algebra on an abelian C-star algebra, okay, maybe I didn't mention, you're right, but every C-star algebra is semi-simple, okay? So in this case, we're assuming there are also abelian, but, every C-star algebra is semi-simple. Let's suppose, that its spectrum is a separable metric space with no isolated points. In this scenario, we can show that there is an isometric and isomorphic, okay? I think something is missing. A copy. I'm sorry. There is an isometric isomorphic copy of A inside of L infinity, where the intersection of this copy with C0 is only 0. Okay. In the case, that A is a C-star algebra, such image is also, such map is also a star isomorphism. That means that preserves the involution. All right. So I didn't mention, but L infinity is also a C-star algebra where the involution is given by the standard conjugation on each entry. So that's one of the very first result that we were able to obtain. All right. As a consequence, by consequence, it seems to be simple, but it's a combination of the proof of the theorem with also this remark. Okay, we can actually show the following. So if A is a separable uniform algebra or an abelian C-star algebra, and if the spectrum has no isolated points, so we can actually show that A is isomorphic, in all this in setting, to a subalgebra of this set. All right, so in particular, okay, such algebra does not exert the classical LP. Now the intersection is trivial. That's pretty much it. All right, so before moving forward, let me just present, some examples of structures, from the hypothesis, if you want to, find examples that fulfill the conditions of the theorem 2.3, I mean, this theorem, so you can choose separable abelian C-star algebra with no compact elements. So essentially, if you want to make your life simpler, you may assume, that your algebra is, is unital. If it's unital, your abelian C-star algebra is C of K with K compact. Right now, you assume, that K has no isolated points. So you have, a bunch of examples of structures fulfilling the conditions, right? We can also consider, the disk algebra. All right, we don't have to enter into the details, but the main point is the disk algebra is not a C-star algebra, so which is, somewhat shows that we definitely consider a larger class just from the C-star algebra, so our class is a little bit bigger. Also, the same holds for this algebra. Okay. And also the analysis algebra. So you do have so many examples that don't fulfill the conditions. So essentially, we do have so many interesting and well-known spaces, right, fulfilling the conditions, right, and you can also identify them as subalgebras or star subalgebras of L infinity, satisfying this condition. So which is somewhat interesting or maybe even surprising. Okay. All right. So the main thing is we have done so far. I hope it is clear to you all at this point, but we have so far only constructed examples of separable structures. We have considered separable Banach algebra, so their image is also separable and what's on. All right. So what we're going to do now, we're going to show that we can also obtain. a variant of this theorem, okay? But in this case, our copy, let's say that a tilde is gonna be non-separable. All right. All right. In order to do it, we're gonna do, you're gonna present a little bit more definition, but again, I just want to present the definitions just to give you a general idea, of the framework. We are not gonna end into technical details, but just to give you some sort of taste what is actually behind. All right. So once again, A is a commutative Banach algebra, associative. All right. For us in this talk, everything is associative. All right. We say that a map from A to itself is a multiplier if it satisfies this condition. Okay, it satisfies this condition. All right. And we're going to denote by M of A, the multiply algebra of A. All right. So M of A is the set formed by all bounded, bounded linear operators from A to itself, which are multipliers. And another thing we should mention, about net is said to be about the approximate identity. It satisfies this equality, at the limit. All right. And the identity is minimal, when such limit of the norms of the elements that generates, the approximate identity is equal to 1. All right. So why I introducing these ideas is because the following. So under some conditions, we may assure that A is actually, an isometric copy. I'm sorry, A contains an isometric copy inside the M of A. Okay, so under conditions, in the case, have a minimum approximate identity. So that's the reason, basically, I have make some comments about such definition. All right. So in this case, we can assure that with that A can be identified with some closed subalgebra of the multiply algebra, right? Also, the other thing we should mention is the following. If A is a C-star algebra, so M of A is also a C-star algebra. So we can also interpret A as a norm closed C-star subalgebra M of A. Okay? And another thing we should mention is the following. If A is unity of C-star algebra, so the multiply algebra A is A itself. So you're not doing anything new. You're not obtaining anything new. That explains why, when you go to the main theorem, we assume that our structures are non-unital, okay? Otherwise, you are basically repeating, obtaining the old results from the previous section, So that's the reason you are assuming they're non-unital, all right? So if you have a separable non-uniform algebra or separable abelian C-star algebra, so if, there are no compact elements, or the only compact element is the 0, 1, then there exists an isometric, algebraically isomorphic star in the case of C-star algebras, copy D of M of A, fulfill the same condition, all right, where D intersection with C0 is just 0. Copy D of M of A in L infinite, all right? The thing we should mention now is the following, all right? If A is a non-unit separable C-star algebra, then the multiply algebra is non-separable. All right. So that shows that we have actually, extend our findings, for a larger class. We are now actually constructing, copies, which are non-separable, but what they also have, the same main property, this intersection being trivial. All right. And the other thing, if A as A, is a non-unit C-star algebra, the multiply algebra of A is CBL. All right. And in this case, L is locally compact, but not compact. All right. Otherwise, if it is compact, it is unit. So you don't have units. You don't want a units. And you can actually, obtain the following result as a consequence. Okay. if we assume that C0L is separable, all right, and with non-trivial, compact elements, so you can also obtain similar results. All right, so we can actually obtain the same conclusion. All right, so nothing new. And the following result can also be obtained. Okay, here, I'm gonna tell you guys, there are some, ideas which are hidden, because you have to explain how you can actually construct some certain maps. All right, from L infinite to BL to N. Okay, so in order to avoid, more nomenclatures and more, more information, I'm just gonna state the results, right? But all the positive results we have obtained before, for L infinite, without C0, we can apply for BL to N without KL to N. Just recall, BL to N is the set of all bounded linear operators from L2 to itself, all right? And KL to N is exactly the set of compact operators, all right? So essentially, we have a result of the same in nature we were obtaining before. This behaves like L infinite, all right? And the other one behaves like C0, right? And I mean, like, because, because for instance, this set is the set of compact elements. So we do have similar results. All right, so this lasts maybe, I don't know, maybe 20 minutes, okay? Let's now explain how we can tie down, our results with this concept of algebrability, okay? The main thing you guys should keep in mind is the following, usually when people have, introduced this concept, they most of the time only took account, generators, minimal generator sets. However, I believe that's common sense, at least for this group, is that minimal generate set is something we cannot afford always. There are so many structures without minimal generating sets. Okay, so from this perspective, we see that maybe it is a better idea, to I don't know if I should say relax, or at least to make some adjustments of the definition, in order to make more, how can I put this, to make more manageable, to consider variants of algebrability and series-star algebrability. Okay, so in order to do this, let us recall a couple of other definitions. Okay, so if we have a Banach algebra and S a subset of A, we consider the set of words. All right, so the set of words of S, as in the usual way, you choose elements of S, you consider the words, and consider, words might mean, but like, the elements, use juxtaposition, you put one by the side of the other one, you have no limits how many times you want to use the same element, and whatsoever. So you can do this, all right? So with this set in mind, we can define, the span of such set, of the set of the words, okay? That generates a subalgebra of A generated by S. If you consider the closure, we have the Banach subalgebra generated by S, okay? And for the C-star algebra definition, I'm gonna hold for a while. I'm gonna explain carefully in the sequence, okay? In this setting, you say that the set A generates A, all right? When satisfies this equality, A of X is equal A, all right? The same holds for the Banach algebra, all right? Generates A as Banach algebra. A remark, okay? If A is an infinite dimensional Banach algebra, so then every generated set of A has to be infinite. So this is a very basic argument, so I'm not gonna to spend so much time on it, but that's important because at some point we're gonna use it. Okay, so if it is infinite dimensional, so every generated set of A as algebra is infinite. All right. Now let's make let's start moving forward to the definition of a generating set for a series star algebra. So usually, what one could do, if you want to consider S as a generator for a C-star algebra, is to do the following. S is a subset, all right, and you consider the closure of the algebra, of all the words, of this set, S union with the S star. Okay, so you consider the elements with S with the involution. However, we are not going to follow this idea, and the reason, okay, I'm going to explain details in the sequence, okay? The definition will be the following. If A is a C-star algebra, we say that S generates A when, the Banach algebra generated by S, is equal A. By SA, I mean, I'm considering just the symmetrical elements. An element is symmetric when the evolution of the element is the element itself. So X star is equal X. So the main point is why to make such a restriction. So we are going to see in remark 3.8 and the proposition 3.12 why we do need to do this kind of restriction for the generator, for the generators. So now before moving to that explanation, let me just recall a definition that can be found in this reference three. Okay, this is the standard way of defining when a set is alpha beta algebrable. So we say that a certain subset M of A is alpha beta algebrable, where alpha and beta are two cardinal numbers, if we can find a subalgebra B of A fulfilling the following conditions. B is a subset of M union 0, the dimension of B equals alpha, and the cardinality of a minimal generated system or a minimal generated set is beta, all right? And we just are going to say that's algebrable if such cardinality is just infinite. The cardinality of the generating the system of generators. All right. This is the standard definition. All right. So if you look to this definition, and if you try to do some comparison with our findings, we can actually notice that our results are directly related to this idea of algebrability. Because in our case, our set M is what? L infinity without C0. So we do have obtained some results toward this direction. Okay. However, from our construction, we do have some sort of problem because as long as we can actually show that we do have copies of so many structures, we have no prior knowledge about the existence or not of a minimal generated system. So for this reason, we see ourselves at some level forced to make some adjustments in such definition. We are going to see a little bit ahead. So just a simple comment, okay. C-star algebras, which is infinite dimensional, may be singly generated as C-star algebras. Singly generated as C-star algebras, not as algebras, okay? Because as algebras, we do know if the algebra is infinite dimensional, cannot be algebra which is infinite dimensional cannot be finitely generated. Okay, that was one of the very first remarks in this last part. Okay, just a comment. All right. Now comes the thing, which is some sort of very technical. All right, but it is crucial, for our better understanding of the results. So, if A is a commutative C-star algebras, we can define actually three sets. We call Gen A, Gen Ban A, and Gen C-star A. Okay, it's the collection formed by all subsets of A that generate A as algebra, Banach algebras, and C-star algebras, respectively. All right. So now, from each set, we can consider the associated set of cardinality of the generators. All right. it is standard to show that this is actually a set as well. So, which is a set of cardinal numbers. And as a set of cardinal numbers, we can always find, the smallest element. All right. So if you can find the smallest element in this case, that means we can find the generator with smallest cardinality. And that can be done, regardless, if there is or not a minimal generating set. So from this point of view, that gives us more freedom. So that's the reason, we are gonna be focused in considering that we're gonna call gen of A, which is exactly, the cardinality of the smallest generating set as algebra, gen B of A, the cardinality of the smallest, generated set as Banach algebra, and the same idea for the gen C star A. All right, so this can be done. All right, so now let's move to the infamous remark 3.8. Okay, why infamous? Because, if we choose, right, a generator set only formed by self-adjoint elements, we can always reduce such set. If we choose a generator set for a C-star algebra with only, self-adjoint elements, so we can always reduce such set. Okay. So the question is, so what's the problem? The problem is going to come in the sequence, okay? Because if we don't make this assumption that the generators going to be all self-adjoint, we are going to lose the next result. I'm sorry. Just this is the following result. Oh, I'm sorry. This result. All right, so if A is a unity commutative C-star algebra and delta A is its spectrum, so we do have this condition. All right, the point is such a result, okay, only so far was only known for finitely generated C-star algebras. But these results only holds, okay, if you assume, all right, that your generators are self-adjoint. Okay, otherwise, if you again look at the remark 3.8, the result does not hold because every time you find a generator with self-adjoint, you can reduce the number of the generators. So that means if you can reduce, we are gonna lose this conclusion. So that's basically the reason why in the literature people are considering generators for C-star algebras as being subset of self-adjoint elements. All right, so I hope that has become clear. Okay. All right, so this I have already mentioned. And now let's see. From our finds, from the comments and whatsoever, okay, we see ourselves, at somewhat, compelled or at least, encouraged, to introduce the following definition, all right, which is somehow, I'm sorry, somehow adaptation of such general definition of algebrability. Okay, we are going to relax this condition of for the system of generators, for the reasons we have already discussed. Okay, so we are going to do the following. Let A be a Banach algebra and D and N two cardinal numbers. You're going to say that such set, get a set A, M inside of A is n gen algebrable. Okay, the same holds Dn gen algebrable if there exists a subalgebra B of A such that B is containing M union 0 and gen B equals N. What that means, the cardinality of the smallest cardinality of a generator for B as algebra is exactly N. This number always exists. That's the main point, So with such definition, if you are able to to construct certain copies, copies inside of certain structures, you do know that such number exists, right? Of course, one thing is to know if the number exists. The other thing is to know who is the number. Now, how to compute it. But those are two different questions. But the main point is we do know that we can find it. So I'm sorry, no, we can find that at least it exists. So that's the reason we're going to consider this variant for our purposes. Okay, so this is a variation of the classical definition of algebrability. All right. As I already mentioned these things. Okay. And another thing I didn't mention, which is quite interesting, is that two minimal generate sets can have different cardinalities. Once again, for you guys, I believe that's quite clear. All right. But when it comes to the smallest cardinality, this number is well defined. All right. So this is another thing, another problem that we can avoid. Okay, if we consider such variation. So, as I have already mentioned, the following results due to Nagisa. All right, so that so far only held, for finitely generated C-star algebras, and we are able to extend such a result, okay, for infinitely generated C-star algebras. All right, so which is essentially the same thing that's over here, right? But for infinitely generated algebras. All right. From the letter, we see that we can define the following concept. Okay? If you have a compact Hausdorff space, we define the set of embedded cardinal of case in the following way. Okay, just note, all right, that we define this based on these relations where we have obtained in the previous theorem. Okay. All right. I think I'm pretty much running out of time, so I'm not gonna to overwhelm you guys with more definitions. But the thing is, we can use some topological invariants, in order to compute this number here, the gen C star A. Okay, and I'm just gonna tell you guys the result. All right, so if A is an abelian C-star algebra that's not finally generated as C-star algebra, so we do have a way to compute, this number, which is equals to the density character, okay, which is the cardinality of the smallest dense subset, okay, of A, which is equal to the weight of the delta A, okay, which is the smallest cardinality of, so if I'm not mistaken, basis for the topology and so on. All right, so the main point is the number is not well defined, but we can also computing use some topological invariants. All right. Similarly, we can define the concept of n C star genalgebrability. That's the same fashion. Okay. I'm not gonna bore you guys with the details. And the main results that we have obtained, of course, here we are hiding so much details, so many things, right? But the main point is the following. If you choose M to be this subset, so M is D1 gen algebrable and D1 C star gen algebrable for all D. However, M is not D and C star gen algebrable if this is a finite number, a finite cardinal. Okay. All right. And we have also obtained the results for C star gen algebrability. But the main thing I believe I should point out is the following. This whole conversation, of algebrability was first motivated by the following fact. Usually people believed that would be very hard, to show that some sort of subset is algebrable or lineable or spaceable. And in the sense that we could construct, subspaces or closed subspaces or infinitely generated subalgebras, all right? Because they had the understanding that, in the finite cases, it is quite simple to construct. But usually this concept was, introduced from the analytical point of view, which if you just consider, the vector space structure, they were absolutely right, to construct, finite dimension subspaces with certain properties were quite simple. However, when you consider the construction from the algebraic point of view, what these results are telling us is that, the troublemaker cases are exactly, when the number of generators, are finite. So this is somewhat quite surprising, from the algebrability point of view. All right, and so far, I have not seen any results of such nature, where you have problems only, when you consider the finite part, which is surprising, all right? And, I believe, I don't know if people are going to be happy with such conclusions, but they are definitely very interesting. And for this, based on these results, we can also endorse such variations of the definitions. Where am I? That also, emphasizes, which that is very important, to consider such variations, because minimal generating sets can exist and have different sizes. For instance, if you consider like CN, the classical the classical finite dimensional algebra. All right. You can find minimal generating sets with cardinality running from 1 to n. So from that perspective, essentially with only one construction, you can introduce the same example with so many different minimal generating sets with different cardinalities. But now if you look just for the minimal one, generating set of the smallest cardinality, that pathology, is expressed exactly in this result. So I guess this is it. I almost ran out of time, so I think that's it. You can also obtain similar conclusions for in this scenario. Okay. Here are the references. So in case any of you wants to see which one I was referring during the presentation. And I guess that's it. Thank you all for your time. Once again, thank you for the invitation, and thanks.
Okay, thank you very much, William, for your presentation. Now it's time for questions or maybe remarks. Anyone? Jobir wants to say something. Okay, Jobir? Jobir, no, he's okay, he's clapping. So any questions? I think there are no questions or remarks. Okay.
I don't know if that's good or bad.
So maybe I will just point that this work was kind of initiated in some non-associative meeting, so I think it's a good thing.
Oh yes, that.
Yeah.
I think we started this like maybe
Victoria.
3 years ago, at least.
We started
Victoria,
discussing stuff, but actually working it was later, right? But the discussions were initiated in some non-associative meetings, so I guess it's a good thing. I will also maybe point that there is some potential non-associative generalizations of the results. Maybe if we consider the last slide, right, and we look at B of H minus K of H, there is also some non-associative analogous of these sets. And even this result also, because we have commutative subalgebras inside the non-commutative subalgebra, maybe we could look at non-commutative subalgebras and all. But yeah, but probably the results will look very different because we will lose all these topological characterizations. But yeah, there is some maybe
we would be forced somewhat to to find a different approach how to make
yeah,
the embeddings, because there is no, maybe if we assume that for certain instructions we do have some sort of bijection property amongst the maximal ideals and the multiplicative linear function. There are some in some seconds, in the non-commutative case, we do have this bijection. I can assure you. I know some examples. I know by I mean I know how to construct.
okay.
That's what I'm saying. So if some sort of similar approach, maybe that similar things could be done. Of course, we do have probably plenty of adaptations because it's not going to be trivial at all. But maybe that could be a starting point, I would say.
Yeah. Okay, so if there are no questions, I think we can finish here. We can end here, right? Okay, thank you everyone for attending this talk. I think it was a great success. Thank you, William. Yeah, that's all.
You're welcome. You're welcome.
We can end here. Okay. Goodbye.
Oh, you're welcome, Antonio.